If we're going to deal with three-dimensional vectors, at some point we're going to come across the idea of the angle between a vector and another one. Now, more generally, if you've got two vectors and you want the angle in between, what you'd need for that, or what you'd find most helpful, is something called the dot product or the scalar product. And that's something that isn't currently on the A-level syllabus, so it's not something you need to worry about specifically, but it recently was on the A-level syllabus, and it will definitely be in the early stages of any course involving vectors that you might come across in later study or life. So if you do engineering or physics, you're absolutely going to be using that and more. But what is still in the course is the angle between a vector and some certain specific vectors, in particular the vector that points from the origin along the x-axis, and the one that points from the origin along the y-axis, and also in 3D the one that points along the z-axis. So we need to understand how to get those angles, and a good starting point is 2 dimensions. What I'm going to work through here is some methods that we can apply in 3D and build up to it from the 2-dimensional case, so we can see why it works and why certain things you might think would work don't quite work. And then I'm also going to give you an overview of how you can use the 3D calculator mode from GeoGebra, available on the web or via the app 3D Calculator from GeoGebra, so that you can visualize it for yourself, move things around and get more of a feel for what's happening. So let's kick off with this one. If you haven't already, pause the video and have a quick go at these 2 questions, and pay attention in particular to the method that you used, and if you did it really quickly and you're confident, ask yourself, are there any other methods? Maybe not as quick and efficient as yours, but was there anything else that you could have done that would also allow you to get the angle? See if you can come up with at least 2 different methods that will find you the angle you're looking for here. Try it, the angle with the x-axis and the angle with the y-axis. When you're done, let's have a look at what we've got. If you construct a suitable right-angled triangle, this becomes a straightforward right-angled trigonometry problem. We can see that vector goes along 3 and up 5, so the logical approach that I'm guessing most people used would be inverse tan of 5/3. You can get the angle straight away between the vector and the x-axis, here shown in red, and of course if you do the opposite way round, you can get the angle to the y-axis, inverse tan of 3/5. That is the most efficient method for this particular situation. But here's another method that you might have used. You could look at the size of the vector, which you can calculate using Pythagoras. It's not a very nice number, but you can get it. 3 squared add 5 squared square rooted. And then, because you know the hypotenuse and you know the adjacent side, I'm thinking about the angle to the x-axis again, the one that's marked in the diagram, then you could use cos of the angle equals the adjacent 3 over the hypotenuse, root 34. And then equivalently, if you switch across to looking at the angle to the y-axis, then your adjacent side becomes the 5, the distance along in the y direction. Now, that doesn't look like the most elegant method, but it doesn't take a huge amount more work than the other one. And it turns out that that version is going to be more useful when we try to generalize to the 3-dimensional case. So let's dive in. So here's a 3-dimensional vector. I'm trying to move this around a little bit so that you can get a sense of exactly what this vector is, what it's doing. 3, 5, 2 means it moves along 3 in the x direction, 5 in the y direction, so far the same as what we had before, and yet at the same time 2 in the z direction. It looks the same from above, but as soon as you start to move it, you recognize that it has some additional dimension. Essentially, it's got an additional dimension. It's pointing up a bit as well as sideways and inwards. That means we're going to find it a little trickier to identify that nice simple right-angled triangle. It's not got the most obvious lengths, let's say. So if you make a right-angled triangle using this, it's not obvious what the distance from the end of the vector to the x-axis would be. It's not just the same as the y-coordinate anymore. It might look like it from this perspective, but as soon as we start to turn it, you can see that because it doesn't just point flat in the xy plane, it points up, we've got a different distance there. So since we're going to have to calculate distances, it kind of makes sense to go with our alternative method that only requires us to know the length of the vector. And we already know from the previous work we've done that it's easy to find the length of a vector even in 3D. So we can apply Pythagoras again to our 3, 5, 2 vector, and we can get the length, root 38, so a little bit different to the last one. Then we can apply this result. Cos of the angle between the vector and the x-axis is equal to 3, which is the adjacent side when we think of it in terms of the right angled triangle formed by the vector, the x-axis, and a perpendicular from the end of the vector to the x-axis. And that gives us 60.9 degrees. That's a little different to the 59 we got before, but we shouldn't be surprised by it if we think about it. This vector sticks into the screen a little way, or out of the screen if you like, depending on which way you're looking at things. It's pointing up from the xy plane a little bit, which means it's harder to get to. You've got to turn further to get to it than if it was lying flat. What about the y-axis? This is exactly the same vector you're seeing here, but I've marked on the angle to the y-axis, the green one, rather than the red x-axis. And we can see that we're getting 35 point something. You might already be wondering, well, we got 60 point something before, we're getting 35 point something here. It's a little strange that those add up to more than 90 degrees, because that certainly didn't happen with the last one. We got two angles that add up to exactly 90. But maybe you can tell why that would be the case. Let's work through it. We still know the length of the vector, that's the hypotenuse. The relevant component of the vector gives the adjacent side. By the relevant component, I mean in this case 5. We want to know how that vector relates to the y-axis. So our right angled triangle now will essentially comprise the y-axis, or at least from 0 to 5 on the y-axis, the vector itself, and then the line that drops down from the end of the vector to the point 0, 5, 0, the point 5 on the y-axis. So we still need the size of the vector, that's root 38 like we saw from before with Pythagoras. The y component is 5, and we're going to use inverse cos of 5 over root 38. And we get our 35.8. Like we mentioned, they don't add up to 90, but if you think about it, that's because we're not just turning part way from the x-axis towards the y-axis and then the rest of the way. That's why the angles added up to 90 for the two-dimensional version. Now we're also turning out from the page and then back into the page. So you are obviously turning more than 90 degrees altogether. If that's a little confusing, let's try a more obvious example. If you turn from the x-axis to the z-axis, completely vertical, and then from the z-axis down to the y-axis, you've actually done two 90-degree turns. If you lift a pen from flat on the table pointing sideways, in line with your spacebar, let's say, and you lift it up so it's vertical, you've turned it 90 degrees. If you then put it down so that it's pointing away from you, perpendicular to where it used to be, then you've turned another 90 degrees. And yet it's only 90 degrees away from where it was before. You could turn it flat with the table 90 degrees clockwise, and it would end up pointing back the same way that it was. So the angles do not necessarily add up to the same thing that they would in 2 dimensions, because you're turning it through that third dimension. What about the z-axis? Well, even though it's harder to visualize, it's just as easy to calculate. We need the z component, so this time we're interested in how much of it is pointing in the z direction, and we need the size of the vector. And again, that z component is going to be the adjacent. It's the side next to the angle. So we're going to incorporate the z component of 2, the size of the vector, root 38, and we still use the same formula. Cos of the angle equals 2 over root 38. We get 71 point something. This is the biggest angle of the ones we've had so far, but maybe you can see why. The smallest angle was the previous one, the angle the vector makes with the y-axis. And that's because the vector is most heavily directed in the y direction. The largest component is the y component, 5. And the second largest is the x component. But the smallest is the z component. That means there's not much of this vector that's pointing in the z direction. There's quite a bit in the y direction, not so much in the x direction, and not very much at all in the z direction. If we were to shrink that 2 to size 0, then it wouldn't be pointing in the z direction at all. It would be lying flat in the xy plane once again. And that would make the angle with the z axis 90 degrees. And you could still use this formula. Cos of the angle equals 2 over root 38 would become cos of the angle equals 0 over root 38. And inverse cos of 0 is 90 degrees. So it still works. This is a generalization from the two-dimensional case, but it also works in the two-dimensional case. That special case of the 3D vector is subsumed within this. That's why GeoGebra is happy to plot 2D vectors and 3D vectors in the same space. It just has the 2D vectors all lying flat in the plane, and then the 3D vector, let's say the vector 340 and the vector 347, well, they're both 3D vectors, but the vector 340 is indistinguishable from the 2D vector 34. You don't need to think of a z component necessarily. Let's look at one more example. You'll notice this one has a negative y component. So although the vector is pointing in the positive x and positive z directions, and quite a lot in the z direction, that's why it's mostly pointing up in this picture, it has a negative y component, so the direction is in the opposite direction to y to some extent. That is reflected in the angles, as you might be able to see already. In general, the principle you're going to follow is this. If you have a vector and you know the three components of the vector, and you're interested in the angles between the vector and the x, the y and the z axes, then these are your formulae. And don't panic, because they're not new. In a sense, you've known them since year 8. These are your right-angled trigonometry formulae. In fact, it's only the cos one. Cos theta equals adjacent over hypotenuse. The adjacent side is the relevant component, because if you're interested in the angle to the x-axis, all you care about is the x-coordinate of the vector. When you drop a perpendicular down from the point of the vector to the x-axis, then the adjacent side you create has length equal to the x component of your vector. The hypotenuse is always just the length of the vector, and that we can get with 3D Pythagoras. Once we're happy with that, it's relatively quick to apply it. So in this particular case, we can calculate the size of the vector. We do some 3D Pythagoras, 3 squared, negative 2 squared, 7 squared, add them all together, square root, 62 square rooted. And then we have cos alpha, 3 over root 62, and so on. You'll notice that cos beta is negative, and that's what we would expect. But it's not going to give us a weird negative angle, because when we do inverse cos, we always get answers between 0 and 180 degrees. The cos graph is positive from 0 to 180. So although we might get obtuse angles from time to time, and we will whenever cos is negative, we won't get any negative angles or anything reflex, for instance. And that makes sense if you think about the situation we're talking about. We want to know how far you need to turn to get from the direction you're facing, if you are this vector, to the positive x direction, or the positive y, or the positive z direction. Now, if you're pointing in the opposite direction to the positive, in this case, let's say the positive y direction, we're pointing slightly in the opposite direction to the positive y direction. So we're going to have to turn more than 90 degrees to get back to pointing in the positive y direction. We could make that more extreme. If we had negative 20 as our y component, for instance, you'd be pointing almost perfectly back along the y-axis. But you can't get more than 180, because if you're pointing perfectly back along the y-axis, no matter which way you turn, you'll be turning so that you're in the direction of the positive y direction. This is the equivalent to saying, if you're standing at the North Pole, which way do you need to head in order to go south? The answer is any direction you like, because every single direction is south, because you'll be heading away from north. Or if you're trying to get from one point on the Earth's surface to another point, and you find that the journey you're going to take is longer than 20,000 kilometers, then your best bet is to turn around and head in the opposite direction, because your journey doesn't ever need to be more than half the circumference of the Earth. You can head the other way and you'll get there a lot quicker. In this case, we can be in the same direction as, say, the positive y-axis, and we'll have an angle of 0. We can be in the exact opposite direction, have an angle of 180, or we can be somewhere in between. There's nothing else. You would never need to turn more. So without further ado, here's our angles, and you can check what they look like on the diagram. Hopefully you've been watching that and trying to get a sense of what's happening in your head. You will find it a lot easier to move this around and see it for yourself. So if you haven't already, I highly recommend downloading 3D Calculator from GeoGebra on your phones. And I'm going to talk through next how you can start quickly and easily drawing vectors and representing the angles between vectors and axes using the GeoGebra app. I'd like to talk to you a bit about how you can use the 3D version of GeoGebra to represent things like vectors and to get hopefully a clearer sense in your head of what's going on when you find things like the angle between one vector and another, or the angle between a vector and the x-axis. We have to go down here. Instead of clicking the big blue button, once you're at geogebra.org, you go down to Powerful Math Apps and you find 3D Calculator. This is also the name of the app you can get if you download it onto your phone. And you can see a tantalizing picture over here on the right of the kind of interesting things you can do if you're able to work with three-dimensional graphs. The most useful thing about it is that you can move the screen around. You can do this just by dragging with your finger or with your mouse, depending on the device you're on, and that allows you to get a sense of exactly what's going on much more easily than if you're just looking at static pictures on a screen. Let me show you what I mean. If we plot the point 43, you can see that the red line represents the x-axis and the green line is the y-axis, and turning it just so, we can pretend the z-axis doesn't exist. It's actually pointing straight out of the screen towards you. But this point, the point 43, is the traditional point 43. It's 4 along and 3 up, but 4 in the x direction, 3 in the y direction. But crucially, it's the same as the point 430. GeoGebra is just assuming that you have a z coordinate of 0, which is why it's been put at a height of 0. It's sitting on this grey infinite plane, the xy plane, all the points that have a z value of 0. So you can think of that point A as being on the floor, a certain distance from the left-hand wall, a certain distance from the back wall, but it's not been lifted up into the air at all. We can see the difference if we try another point, the point 432. From a certain perspective, this doesn't look any different. It's still 4 in the x direction, 3 in the y direction. But of course, because it's up, it is above the point A, and moving this around a bit will help you to get a clearer sense of exactly what's happening. The point B is somewhere higher up than the point A. Now let's get to vectors. If you type vector in here, you'll see there are two options. You can get a vector between 2 points. Vector A, B will give you the vector from A to B. You can also get a vector directly to a point. The default starting point is the origin, so you can get the position vector, essentially. Vector A will give you the position vector of A, which is by default marked on going from the origin to the point A. And if we ask for the vector B, it gives me the vector that takes me to B. Now, I'm interested in both of those vectors because I'd like to try to represent what's going on when we look at the angle between a vector and a particular axis. Remember, as far as we're concerned, in 2 dimensions, A and B kind of look the same. So you might be expecting that the angle between the vector and the x-axis should be the same. Surely we've got enough information. We can just look at the x-coordinate and the y-coordinate and calculate the angle between the vectors. Turns out it's not quite that simple. To help us get this angle more easily, I'm going to define another vector. I'm going to have a vector which takes me to the point, let's say, 600. That will go from the origin to the point 600. Oops. If you just enter the numbers 600, it's going to get confused, but if you enter them in extra brackets, so you've got the vector corresponding to a point, the point being 600, it'll understand just fine. There's the vector. That vector lies exactly along the x-axis. So I'm effectively, when I compare things to that vector, which has been called vector A, I'm comparing them to the x-axis. Now if you type in angle, there are lots of options here, so feel free to play around, but the one that I'm most interested in is the angle between a vector and another vector here, and it'll give me the most efficient angle from one vector to another. Now the vectors I'm interested in the vector OA, which has been called V here, and the vector I've just created, the vector A. So the angle between vectors V and A, and there it is, 36.87. We can check here, and you can confirm for yourself if you do something simple like inverse tan of 3/4 or inverse cos of 4/5 or inverse sine of 3/5. Any of those should give you 36.87. That's definitely the angle between the vector OA and the x-axis. But hopefully you're starting to appreciate and recognize why, if we do the same thing for the angle between the vector OB and the x-axis, we get a different number. We get 42 point something. What's happening here is that that vector from O to B is in some sense further away from the x-axis because it's been lifted up in the z direction as well as moved along. So you've taken your pen, if you like, that was lying at an angle on the table, and you've lifted the end of it, and now the pointiness of that corner is not quite the same. It's a wider angle that we've got here. You can't see these numbers very clearly, but this is the angle we've just created. The 36.87 is the angle lying flat on the xy plane, and the 42.03 is this new angle that we can see angling up and sideways as well as in the xy direction. And we can probably see that more exaggeratedly if we change how far B goes in the z direction. If you either come back up here where you've defined B and redefine it by changing a 2 to a 3 or something like that, it'll just shift B up and the angle will change accordingly. Alternatively, and this is very useful if you've got a big long list and you can't remember where it is, you can type capital B equals and then redefine the point. We want 4, 3, 6, let's say, and suddenly B is way up here and the angle is significantly bigger. And it should be, right? That point is now going quite a long way up. In fact, the more up it points, the closer it's going to be to being the same as pointing in the z direction, which is actually perpendicular to the x-axis, even though when we look at it from this direction, the angle might appear to be the flat angle, the 36.87. Turns out we're now getting much closer to 60 degrees because of how far this vector points upwards. Hopefully that's given you a bit of an insight into what's going on with angles in 3 dimensions.